So can I say this in our case? So we are saying that HA B1, at least one of the BI is not equal to 0. Okay, if it may happen that all of them are not equal to 0, it may happen that only one or only two will be not equal to 0. So the null hypothesis says no relationship, alternative hypothesis says that there is relationship. Okay, now so for every hypothesis testing we have to have a formula. Okay. We need to find out what is the formula that we have to follow for this. What will be the formula? So for this, what would be the formula? Okay. Now it so happens that the formula is slightly complex, okay, and I have not covered the F distribution till now. So F distribution is still pending. I have to cover F distribution. We'll see F table. Okay, but we have to find out the formula. So what we see the formula over here. Okay, the formula is given as F is given as, okay, mean sum of square regression. That is mean sum of square regression divided by mean sum of square error. Okay. So what is the value of mean sum of square regression? So going back to the PowerPoint, we had said that, or let's see this. I know that we have discussed this ANOVA table in the previous class. Okay, let's try to see this ANOVA table. Okay, in this ANOVA table, what we are saying is, okay, you have degree of freedom. Okay, K, you have degree of freedom n minus k minus 1. Total degree of freedom is n minus 1. This is your, if I write over here, this is your explained or your regression part, and this is your error part, and this is your total. So your degree of freedom of explained is k, that is the number of independent variable. Degree of freedom of error is n minus k minus 1. The degree of freedom is total number of the sample size minus the independent variable minus 1. So your total, it should become n minus 1. Okay, and over here you are saying that it was sum of square regression. Okay, it was also called as explained sum of square. Okay, here it was total sum of square. Here you are saying the sum of square error, or you are saying that residual sum of square. Okay, these two were the same thing. Sum of square error or residual sum of square regression, or explained sum of square. Okay, here you had mean. So here you had mean sum of square regression. What is the formula of mean sum of square regression? The mean sum of square regression, the formula was sum of square regression divided by k. Okay. Here the formula of mean sum of square error was, we had seen this also today, sum of square regression divided by n minus k minus 1. What is k? K is the number of independent variable. Okay, so your k is the number of independent variable. You have sum of square regression by k, sum of square error divided by n minus k minus 1. K is the number of independent variable. So another way of writing this formula F would be to do this. Okay. Now one thing that we have, the way F distribution is there, F distribution has to be always positive, or sorry, always positive is there, but the way we have created it is always greater than or equal to 1. So F distribution is always greater than or equal to 1. Okay. Now over here you will find that, okay, since this number is very large, okay, n minus k minus 1, ideally we want to have sum of square error less than this. So what will happen is, the numerator is greater than the denominator. This is what you will see, that numerator is greater than the denominator, and most of the time, and you will find that F will be greater than 1. Okay, so this is a formula that is given to you. Okay, now you have to do a F test. Okay, so for F test you have to find out first the critical value. So first you have to find out the critical value. How you will find out the critical value? For that critical value you have to look into the table. Okay. Now unlike the Z distribution or T distribution, you have separate F table for separate different alpha. So for different alpha you have separate F table. Okay. So what we have is, okay, in the F table goes like this. So you have numerator degree of freedom going across and you have denominator degree of freedom going down. So down you have denominator degree of freedom, here you have numerator degree of freedom, and what you have is you have alpha is given to you. Let's say alpha is, okay, 0.505. Okay, it means that this alpha, it is like always a one-tailed alpha. So they will always give you one-tailed alpha. So it means that, and one-tailed also means right-tailed. So what you have is, they have been given that this is 5%. Okay, so if this is 5%, the table value, what, let's say you are having in the numerator, the degree of freedom comes as, let's say, 5, and let's say the denominator degree of freedom comes as 20. So what you will see is this 5 coinciding with this 20, whatever the value, that will be the value over here. So that would be the critical value. Okay, from the formula you will found out the formula value. The formula value can be here or it can be here. Okay, if it is here, you will be rejecting the null. Here you will be accepting the null. Okay, when you are accepting the null, it means no relationship. When you are rejecting the null, it means that there is some relationship. At least one of the BI are not equal to 0. So let's see the formula. So this is the F table. Okay, so what you have over here, they have given you the degree of freedom over here. So this is your df1, this is your df2. Okay. Now if you see this table, okay, you will be able to appreciate the fact that, okay, here no values of f are less than 1. Everywhere it is greater than 1. Okay, here the minimum value here it's 1.03. Okay, but it is for 1000 and greater than 1000. For infinity versus infinity, if you see the infinity versus infinity, okay, so if you see infinity versus infinity, the value is 1. Okay, no matter what alpha is, here alpha was 0.05, here alpha was 0.1. Okay, degree of freedom infinity versus infinity, it is 1. That means the f value cannot be less than 1. Okay, the f value cannot be less than 1. And this alpha that they are talking about is the probability in the right tail. So this shaded region is alpha. Alpha is 0.1 over here. So this is the probability in the right tail. Okay, so the F distribution is a right skewed distribution used mostly in analysis of variance. What is your analysis of variance? ANOVA. ANOVA full form is analysis of variance. You use over there. Okay, now, okay, so you will be getting some type of this, and you will have to understand that, okay, whether F statistics is critical, whether you are able to reject or accept, and whether there is a relationship there or not. Okay, so we can take an example, okay, and we can see that whether that value is, whether there is something. So let's say we are doing a 3 variable. Okay, so if we are doing a 3 variable, okay, let us try to find out this ANOVA. Okay, so here we have degree of freedom. Okay, for degree of freedom for regression will be how much? If your independent variable is 3, so the degree of freedom over here will be 3. Okay, k. So your k is 3. Okay, your error will be, let's say we have a sample size. Sample size we are doing a testing on let's say we are doing a sample size testing on, assume 15. Assuming we are doing testing on 15. So what will be this value? Degree of freedom will be n minus k minus 1. So it will be 15 n minus k minus 1 11. Okay. Now let's say the total sum of square is 1000. The total sum of square is 1000. Okay, and this guy is 800. This guy is 200. Okay, so this is your sum of square. The sum of square is this. What would be your mean sum of square? This mean sum of square will be how much? This divided by this. So it will be 800 by 3. This will be 200 by 11. What would be our f value? F value will be this. Okay, so it will be 800 by 3. 800 by 3 divided by 200 by 11. If you try to find out, f will come as 4 into 11 divided by 3, so roughly 15. So the value of f you are getting is roughly 15. Okay. Now what you have is degree of freedom. Numerator is 3, denominator is 11. Numerator is 3, denominator is 11. We will say that f value will be 2.66023. So what we have is, in this testing, the critical value is 2.66. The formula value is over here 15. So what we are doing is, what we say is, we will reject the null. When I am rejecting the null, it means that I am saying that at least one of the BI, at least one BI is not equal to 0. So this is the way you will be doing your testing. So let me explain to you what we are doing. So this is your ANOVA. This is your ANOVA table. This is the ANOVA table. Since you are doing a regression with 3 variables, you have done independently B1, B2, B3. You are seeing all of them are 0. But you are seeing that R square is 80. R square 80% cannot come if these guys are not able to explain. Okay, that can happen only when there is a relationship. However, the t-test is incapable of testing that, because t-test is doing individually. So what you say is, like, you will try to find out whether this mean error are very high or very low. So you will do this F testing. In F testing, what you have is, in one side you have the regression, okay, on other side you have the error. Okay, you want to understand whether regression is more or the error is more, whether you are able to explain the things or not. Okay, so you have a formula. So every hypothesis testing has to have a formula. Hypothesis testing has a formula over here: mean sum of square regression divided by mean sum of square error. You will do this. You will find out the critical value. You will find out the formula value. You will find out the critical value from the table. You will plug it and you will see whether there is a problem or not. Okay. However, there are a couple of things. So remember, like, I did not touch this F test when we are doing the hypothesis testing. There are some things which we have to understand. So but before that, I want you to solve one more problem for me and tell me whether there is some relationship or there or not. So ANOVA table. So you have explained degree of freedom comes as, there are 6 variables. Okay, and your sample size that you have taken, the sample size that you have taken is 10. The sample size that you are working with is 10. So your sample size is 10. Okay, the sum of square over here that is given is 600. Sum of square error, so this is for regression and this is for error. So this is the output of the ANOVA table. Okay, I am not giving you a lot of things. So n equal to 10, okay, is given to you. Okay, actually I should have done, okay, we have to find out with precision will be higher. So please note down this. Degree of freedom is 6, sum of square 600, 400, n is 10. Okay, so we have degree of freedom 6, sample size I have given you as 10, okay, or maybe like make it like 12. Sample size make it at 12. Okay, here this is your 600. The explained part, regression is 4 part. Okay, we have to test with alpha. I want to test with 90, I would say 95% confidence interval. Okay, with 95% confidence I want to test whether there is a relationship there or not. Please note that when you are testing for 95%, okay, what you have is you have some things as b1, these are equal to 0 and this is not equal to 0. So essentially you have a two-tailed test, but the way F table is created, F table is only a single tail test. Okay, make sure you understand this. F tail is always a single tail test. It is never a double tail test, and always a single tail, and that to right tail. So you have a right tail test always. Okay, when you are doing with 95%, okay, what is this? Can I say it will be 2.5%? How you distinguish between a two-tail test and a one-tail test? So you are doing suppose some two-tail test. So two-tail test here it will come as 2.5%. If you are doing a one-tail test, what would happen? If this is 95%, this would have become 5%. That is how you distinguish. So when it's a two-tail test and you have 95%, that means both the legs have 2.5%. Okay, then you will refer to this. However, if it's a one-tail test, this guy is 95%, so you will have to refer to the table which is alpha has 5%. Okay, in this case the test is two-tail because you have b1 equal to 0, b1 not equal to 0. The test is two-tail. Okay, now you have to find out whether we will reject the null or we should accept the null. So here it will become how much? 600 divided by 6, it will become 100. 400 divided by 12 minus 6 minus 1, it will become 5. So 12 n minus k minus 1. So 12 minus 6 minus 1, 5. So 400 by 5, it will become 80. So your f will become 1.25. Okay, and if you see with this 2.5%, what would your degree of freedom of numerator? 6. Denominator it would be 5. The f value comes as 6.977. So what you will be seeing is 6.977. So this will be your critical value will be 6.977 and our value is 1.25. So we will not be able to reject the null. Okay, and we'll say that there is no relationship. Okay, so t-test was correct. Please note that t-test need not always be wrong. Okay, collectively also we are not able to explain the concept over here. Okay, so collectively also we are not able to explain. So that means there is no relationship. Okay, so if it is, let's say this, then next concept that we have. Okay, in any problem. So can we say that, okay, what is f test and how we are distinguishing f test from a one tail and a two tail? How one tail and two tail has been distinguished? One tail and two tail are being distinguished only using this concept. Otherwise there is no difference in the one tail and two tail. Now another concept that we have to understand in this case is, another concept that we have to know is r square. So what about r square? Okay, so r square, so you have r square. Okay, please note that it has been seen that if you have y equal to a plus b0 plus b1 x1 and you have then y equal to b0 plus b1 x1 plus b2 x2, what happens is the value of r square, it increases from here to here. Okay, so you may say that, okay, x2 is able to explain this more. Okay, when you add another variable x3, b3 x3, r square again increases. Okay, so what happens is this value of r square keeps on increasing. Okay, many times it may happen that this variable is not adding any value. It is not adding any value. Okay, but it is not adding any value, but because of the interaction of x1, x2, x3, because of the non-linear interactions among these, what happens is there we start thinking that so we start thinking that this x3 is adding some value. Okay, so that means this r square that you are getting is not correct measure. So this r square is not correct, r square is wrong. Okay, so because of the interaction, because of the noise among these variables, you start thinking that it is adding some value. In reality the value is not there. Okay, so the idea to remove this is to use, as Vinith has said, to use the r square adjusted. Okay, now what is this adjusted r square? Okay, so firstly let's look at the formula of this r square adjusted. Okay, so the adjusted r square, this looks as a very difficult formula, but what we say is, think about this. Okay, we write this formula as this. Okay, 1 minus r square adjusted, okay, will be equal to n minus 1 divided by n minus k minus 1 into 1 minus r square. This r square you are getting from the actual regression. Okay, this typically keeps on increasing as you add more and more variable. Okay, but in reality there is no this. You might start thinking that there is a relationship that is being added. As Ali has said that you might like take inflation, interest rate, okay, unemployment rate. You might want to take many of the things and you want to find out the stock return. Okay, what happens is initially when you are adding the variables, they are adding value, but as when more and more variables are being added, the value is reduced. So what we have is the concept of r square adjusted is we are trying to remove the impact of the independent variable. So what we do is we compute this r square adjusted. Okay, so this is a formula. Adjusted r square is this. Okay, what we have done is we have tried to simplify. So 1 minus r square adjusted is 1 minus r square n minus 1 by n minus k minus 1. So you will be able to remember this way. Okay, so what we say is, think about it. Okay, you have r square. When there was one variable, the r square was 80. Okay, when you had two variables, the r square was 85. Let's say 90. When the r square number of variable was 3, let's say r square was 95. Okay, when 4, let's say 97. When 5, let's say 98. When 6, let's say 98.5. Okay, it might happen that only the addition was done. These are the only good variables. After that the variables are not good, but r square is keep on increasing. Okay, what we need to do is we need to compute the value of r square adjusted. Okay, if we compute this r square adjusted value, we'll be able to identify whether these are adding value or not. So the r square adjusted value is given as 1 minus r square adjusted n minus 1 by n minus k minus 1 1 minus r square. Okay, please note that this value is r square in percentage. Okay, decimal. So I've just given this. So what you have is, let's say the sample size is 10. We are talking 10. So over here 1 minus r square. Let's say we want to find out for this. Okay, or we want to find out for this. What is the this and this we want to find out. Okay, 1 minus r square adjusted, 10 minus 1 9, 10 minus 3 7 into 1 minus 0.9. So this is 0.1. Okay, so this is how much? 0.9 by 7. So this is roughly 12 13. Okay, r square is 0.87. So the adjusted r square is 0.87. So here r square is 0.8. This r square is 0.87. So this has increased. Here it was saying 80 and 98, but here it is 80 and 87. It has increased. So we will use this second independent variable. Okay. Again, I want to find out r square over here. Okay. Okay. The idea was that The idea was that you have 80, 90, 95 when you have the second variable. When you are talking about 10, 10 minus 1, n minus 1, n minus k minus 1 into 7 divided by 1 minus r square, which is 95 over here. Okay, and this is your 1 minus r square. So what we will say is, if r square adjusted, okay, r square adjusted will be typically lesser than the r square. Okay, and if r square adjusted is increasing, we will be adding the variable. However, if r square adjusted is not increasing, we will not add the variable. Okay, because that variable is not adding any value. So let's see this. Okay, I had given a problem. I think so. I had one problem for you guys. Okay, this is a problem. How much it would be? So runs are for 5 independent variables. So you have k equal to 5, 36 month. So it's a monthly. So your n is 36, k is equal to 5. The total sum of square regression is 400. Error is 100. Your r square simply would be 400 divided by 500, because total is 500. So this would be 0.8. Okay. Or 80% is your r square. What is your r square adjusted? R square adjusted would be, it would be how much? N minus k minus 1, n minus 1 divided by n minus k minus 1. So 35, n minus k minus 1, 30 into 0.2. So 6, 7. So 1.4 divided by 6. So it would be r square adjusted would be 1 minus 1.4 by 6. So it will be 4.6 by 6. Or it would be less than 0.8. Now the idea is very simple over here, that you compute r square adjusted. You are trying to remove the impact of the number of independent variable that is added. So n minus k, this is the number of independent variable that is increasing. You are removing that impact and you are finding out the new r square value. Okay, now only you will add a variable. So we had drawn that matrix over here, 1, 2, 3, 4. Okay, so we will keep on adding a variable till r square adjusted is greater. So if this is x1, this is x2, x3, x4. Okay, and this r square adjusted value is r square 1, r square 2, r square 3, r square 4. We will add r square, we will add this x4 variable only when r square adjusted 4, which is this adjusted value, is greater than the r square 3. Okay, if this is not greater, that means this variable is not adding any value. Okay, that is the idea. The addition or the value addition comes only when the r square adjusted is more than the previous r square adjusted. Okay, is this clear? So please note that, know the formula. You have to remember the formula of computation of r square adjusted. So construct and perform a interpret hypothesis testing for a single coefficient. Okay. Single coefficient, we know that single test. Multiple coefficient for more than one. Okay. Describe and interpret what is F statistics. Okay. We'll see that interpret the homoscedastic only F statistics. Okay. Describe and interpret test of single restrictions involving multiple coefficients, that is the F test. Okay. Describe and sets for multiple coefficients, confidence test. Okay. Sets, sorry, and we will cover this omitted variable bias. We have computed r square and adjusted r square in multiple regression. So see the idea that if you have covered the simple regression part very well, okay, if you covered a simple linear regression part very well, multiple linear regression part is not that difficult. Okay. It is not at all difficult if our simple linear regression part is over.